Welcome to segment 0 of our Deployed Engineer for Sustainability. This masterclass is not designed to turn you into an engineer in 90 minutes, and it is not a compressed version of the full program. Its purpose is more important at this stage to show you what this role actually does, why it matters, and what professional value looks like when sustainability requirements have to survive contact with real enterprise systems. Throughout the session, keep two visual spines in mind. The first is the capability progression. Know, integrate, build, deploy, prove. Knowing still matters, but knowledge by itself is becoming easier to access. The differentiator is whether you can connect systems, create a working capability, put it into operation, and defend the output with evidence. The second spine is the operating chain shown across the slide. Requirement, data, integration, workflow, AI or logic, deployment, observability, evidence, and outcome. We will use one work case, the TerraWorks supplier carbon implementation system, and repeatedly move through this chain. By the end, I want you to be able to look at a sustainability requirement and see not only the policy or the calculation, but the operating system that must exist behind it. The role we are exploring is the professional who makes sustainability systems actually work inside messy enterprise environments. That is the standard for everything that follows. Next, we move to Masterclass Roadmap. Here is the journey for the next 90 minutes. We begin with the opening thesis. Content is cheap, working systems are not. Then we clarify where a forward deployed engineer sits relative to product management, sustainability consulting, data engineering, software engineering, AI engineering, and solution architecture. After that, we introduce TerraWorks. The business request sounds straightforward. Combine procurement data, supplier evidence, carbon methodology, and some AI so category teams can prioritize suppliers and reduce analyst effort. Instead of giving you a polished solution immediately, we will expose the problems hiding underneath the request. The middle of the masterclass moves through integration and build. Messy data, canonical schemas, reconciliation, APIs, workflows, deterministic logic, and governed AI. We then move from a prototype mindset to deployment and operations, environments, health checks, monitoring, evidence lineage, human gates, and operating ownership. Finally, we connect the masterclass to segment 1, where the learner stops observing and starts building. The objective is not simply to explain the FDE role. It is to show a sustainability requirement becoming a working enterprise system, step by step, with the controls that make the result usable and defensible. Next, we move to content is cheap, working systems are not. Start with the uncomfortable observation on the left. AI can already explain the GHG protocol, summarize BRSR, generate SQL, draft an API, write Python, produce a Docker file, generate a RAG example, and create a dashboard. None of those capabilities should be dismissed. They are useful and they are improving quickly. But look at the right hand side. Professional value is moving up the implementation chain. Know means understanding the requirement and the concepts. Integrate means connecting real systems, identities, permissions, data formats, and constraints. Build means creating pipelines, services, rules, workflows, and AI assisted capabilities that actually operate. Deploy means making those capabilities secure, reliable, recoverable, and usable by other people. Proof means showing exactly what happened, why an output can be trusted, and whether the system changed a business or sustainability outcome. This is the distinction to carry through the course. Generated components are not the same as a working operating system. A code snippet may be correct. An architecture diagram may look convincing. A dashboard may be beautiful. But if the data cannot be reconciled, the service fails silently, the method version is unknown, or no one can reproduce the result, the enterprise problem is still unsolved. So the opportunity is not to compete with AI on producing more content. It is to become the person who can make the pieces work together. Next, we move to two kinds of professional differentiation emerge. Inside the broader Sustainability Digital Innovation Hub, two professional differentiation paths emerge. They overlap, but they are not the same job. The product path moves from understanding to deciding, designing, prioritizing, operating, and proving. A sustainability product manager asks what capability should exist, for whom, why it matters, what should be built first, and how value or adoption will be measured. The implementation path moves from understanding to integrating, building, deploying, operating, and proving. The forward deployed engineer asks how the capability will actually work inside enterprise systems. Where does the data live? What interfaces exist? What fails? Which rules are deterministic? Where can AI safely assist? What must be monitored? How is evidence retained? This master class follows the second path that does not make it more important than product management. In strong teams, product and FDE work together. Product helps ensure we are solving the right problem. FDE helps ensure the chosen capability can survive enterprise reality. If you are listening and you keep asking questions about integration, failure, deployment, data quality, and proof, that is already a useful signal about your natural fit. Next, we move to the recurring operating chain. This operating chain is the backbone of the entire master class, so I want to slow down for a moment. A requirement is not yet a system. It is a mandate, request, decision, need, or user outcome. Data asks what facts are required and where they come from. Integration connects systems, files, permissions, and contracts. Workflow turns rules into state changes, tasks, reviews, approvals, and escalation. AI or logic is where we decide what should be deterministic and where probabilistic assistance adds value. Deployment moves the capability into a controlled environment. Observability tells us whether the system, the data, and the workflow are healthy. Evidence preserves the source, version, decision, and audit trail. Outcome asks whether any of this changed a real decision or business result. Notice the order. If we jump from requirement straight to a dashboard, we skip most of the engineering problem. If we jump from document straight to an LLM, we may automate uncertainty rather than control it. Every TeraWorks slide will connect back to this chain. When you see a component, ask where it belongs in the chain, what comes before it, what depends on it, and what evidence it must produce. A generated artifact becomes enterprise capability only when it survives this full operating chain. With the operating chain established, we can now look at the FD inside the wider sustainability technology team. Now we can define the role more precisely. A forward deployed engineer for sustainability operates at the intersection of sustainability domain knowledge, enterprise data, software, AI, product operations, and business stakeholders. On the roadmap, notice two dimensions. The first is problem proximity. How close are you to the business requirement and the messy operating context? The second is implementation ownership. Are you mainly advising or are you directly responsible for making something work? The FDE sits high on both. The role is close to the business problem, but it also owns implementation outcomes. That is why it cannot be reduced to software engineer plus sustainability vocabulary. The FDE has to translate between different worlds. A sustainability team may describe a methodology requirement. A data team may describe source system limitations. A product team may describe the desired workflow. Security may constrain access. Operations may require a support model. The FDE has to align those realities into a working system. The operating questions on the right are a useful mental checklist. What decision are we improving? Which systems contain the data? How do we reconcile them? Which APIs are needed? What should be deterministic? Where can AI help? What requires human approval? How will we deploy it? How will failure be detected? And can the final output be reproduced and defended? Those questions are the job. Next, we move to same sustainability request, two professional lenses. Let us make the product management and FDE distinction concrete using the same sustainability request. A sustainability product manager might ask, who is the user? Is this the right problem? What belongs in the MVP? What requirement matters most? What outcome proves adoption? And what should the roadmap look like? Those are essential questions because building the wrong capability efficiently is still failure. The forward deployed engineer looks at the same request and asks a different set of questions. Where is the data? How do the systems connect? What breaks? What should remain deterministic? Where can AI safely help? And how do we prove the output? Think of this as two lenses on one enterprise outcome. Product management decides what capability should exist and why it deserves investment. FDE makes that capability work inside the customer's operating environment. There is deliberate overlap around evidence and outcomes. Both roles should care about whether the solution is trustworthy and valuable. The difference is emphasis. The FDE is accountable for the implementation path between intent and operation. If that path is the part that interests you most, the rest of this masterclass will feel increasingly familiar. Next, we move to TeraWorks Supplier Carbon Implementation System. Now we introduce the case that will stay with us for the rest of segment 0. TerraWorks leadership gives us a request. Build a working supplier emissions capability that integrates procurement data, supplier evidence, and carbon methodology so category teams can prioritize suppliers, identify data gaps, and track engagement. Leadership also wants AI to reduce analyst effort. An AI assistant can generate many attractive pieces in minutes. It can propose an architecture, draft an API, create a SQL schema, write a Python pipeline, design a questionnaire, outline a RAG solution, and mock up a dashboard. That is useful acceleration. But the right side of the slide shows why the enterprise problem remains open. Supplier identities do not match. Source data is incomplete. Access is constrained. Systems use different formats and APIs. Method versions change. Network calls timeout. Exceptions require investigation. Approvals require separation of duties. Deployments need controlled promotion. Monitoring has to reveal failure. Evidence has to be linked to outputs. And someone must own the system after launch. This is the moment where the FDE mindset begins. Instead of asking, can I generate the components? Ask, what conditions have to be true for the entire system to work reliably? TerraWorks will be our laboratory for answering that questions. Next, we move to TerraWorks system context. The first thing an FDE does is widen the view. The business request sits in the middle of a system context, not in isolation. On the source side, TerraWorks may have an ERP holding supplier masters and purchase orders, a procurement platform holding category ownership and contracts, finance data holding spend and currency context, a supplier portal holding declarations and evidence, a document repository holding files, a factor library holding methods and versions, and an ESG data store holding historical sustainability information. On the decision side, category teams want prioritization, sustainability teams care about method integrity, procurement operations care about supplier engagement, data and IT care about system behavior, leadership wants outcomes, and risk or audit wants evidence. The FDE sits at the boundary between these two worlds. The job is not simply to move data from left to right. The job is to preserve meaning, ownership, controls, and decision context while doing so. This system context view prevents a common failure mode, treating the visible application as the entire solution. In reality, the application is just one surface on top of source systems, workflows, rules, people, and evidence. Now that the system context is visible, we can begin with the first hard problem, enterprise data. We now enter the integration phase, and this is where many sustainability implementations become difficult. The visual shows a simple looking pipeline. Multiple sources are normalized, matched, validated, reconciled, and then unresolved problems are routed to an exception queue. The simplicity of the arrows hides the real work. Look at the mismatch examples. One system knows a supplier as soup 10,458 and another as vent 7,782. One stores kilograms while another stores tons. One factor library still points to a 2022 version, while another process uses a 2024 version. Supplier names vary. Evidence may be a PDF in one place and an image in another. Reporting periods do not align. These are not cosmetic issues. Each mismatch can change a calculation, duplicate a supplier, apply the wrong factor, or create a false sense of completeness. The FDE response is to make the controls explicit. Canonical schemas, identifiers, unit normalization, validation rules, data contracts, and lineage. Notice the design principle here. Uncertainty should become visible system state. If something cannot be safely reconciled, it should move into an exception queue with an owner and a resolution path, not disappear inside a spreadsheet cleanup step. Integration is where sustainability logic becomes governed data behavior. Next, we move to source system reality. No single clean truth. Let us break the source problem down system by system. The ERP may provide supplier masters, invoices, and purchase orders, but identifiers can be incomplete and business units inconsistent. The procurement platform may know contracts, categories, and supplier owners, but its category hierarchy may not match finance. The supplier portal contains questionnaires and evidence, but submissions are often late and files are unstructured. The factor library may contain valid emission factors, but methodology versions change over time. The ESG data store may contain historical emissions and targets, but its reporting periods may differ from spent data. The important idea is that the data is not one thing. Every field has an owner, a source, a version, a period, and a confidence level. So the first FDE move is source clarity. What system owns which fact, which source is authoritative for this decision? What happens when two systems disagree? Which versions are valid? Who is allowed to correct the value? If these questions are not answered, later calculations and AI outputs may be technically sophisticated but operationally weak. Next, we move to canonical schema, the bridge from fragments to facts. A canonical schema is one of the most powerful tools for moving from fragmented enterprise data to consistent system behavior. Here we define a common representation for the TeraWorks domain. A supplier has a legal entity identifier, supplier identifier, name, hierarchy, and country. Activity has a type, amount, unit, period, and source system. A factor has an identifier, method, version, unit, and validity period. Evidence has a document identifier, owner, source, version, hash, and status. A calculation records the run, rule, version, inputs, output, and reviewer. An exception records the type, severity, owner, state, and resolution. The point is not that these exact fields are universally correct. The point is that the system needs a stable language for exchanging facts across services. Without a canonical model, every integration creates its own interpretation. A kilogram may become a ton at one boundary but not another. A supplier may be merged in one service and duplicated in another. An AI extraction may produce a field name the calculation service does not understand. A good schema turns implicit assumptions into explicit contracts. That is how fragments become facts that can be validated, traced, and reproduced. Next, we move to work reconciliation example. Now look at the reconciliation table as if you were responsible for production output. The supplier identifier differs across two sources. The FDE does not simply choose one. The system creates a cross-reference or golden record under a controlled rule. Currency differs, so the conversion has to use an agreed FX source and date. Units differ, so quantities are normalized before factor application. Factor versions differ, so the system must require an explicit method version decision rather than silently using whichever record arrived last. Reporting periods differ, so the system either aligns them under an approved rule or routes an exception. This is why reconciliation should not be dismissed as data cleaning. Reconciliation is a control mechanism. It determines whether two records represent the same entity, whether values are comparable, whether calculations are methodologically consistent, and whether the output can be trusted. A mature FDE implementation captures the rule, the decision, the version, and the unresolved gap. The goal is not to make the dataset look clean. The goal is to make every transformation explainable. Next, we move to exception queue, make uncertainty operational. Good systems do not pretend that imperfect data disappears, they make uncertainty operational. In this example, the queue contains supplier ID mismatches, currency differences, unit differences, missing activity data, duplicate records, and conflicting periods. Each type has an owner. That ownership matters because different problems require different authority. A data steward may resolve identity, a finance rule owner may define currency treatment, a method owner may decide how units or factors should be handled, a supplier owner may need to request missing evidence. The operating pattern is simple: detect, classify, resolve, and evidence. A validation or reconciliation rule detects the issue. The system classifies severity, owner, and due date. A reviewer resolves the issue or records an assumption. The action is logged with a version and reason. This turns an exception queue from a dumping ground into a governed workflow. It also creates an important management signal. If a particular exception type grows every week, that may indicate a broken upstream process, not just more work for analysts. The FDE therefore designs exceptions as first-class system behavior. Next, we move to integration controls, turn data into governed inputs. We can now summarize the integration controls that TeraWorks needs before the build phase can be trusted. The canonical schema gives us one domain model. Identifiers allow golden records and cross-references. Unit normalization ensures that measurements are comparable before calculations. Validation rules test completeness, range, and business logic. Data contracts define ownership, schema expectations, service levels, and change management responsibilities. Lineage preserves the path from the source fact to the reconciled fact. Each control reduces a different kind of ambiguity. Together, they narrow the distance between messy enterprise input and defensible output. This is an important career insight as well. Sustainability knowledge becomes valuable in a technical role when you can turn concepts into controls. Knowing that a factor version matters is domain knowledge. Designing the data field, validation rule workflow, and audit trail that enforce the version is FDE work. That is the shift from knowing to integrating. Once the inputs are governed, we can move from integration into build. Now we move from integration into build. The architecture on this slide is deliberately layered. At the top are the source systems, ERP, supplier portal, and factor data. Ingestion and APIs bring data into the controlled boundary. Validation and reconciliation establish whether the inputs are usable. Calculation and business rules apply deterministic methodology. AI-assisted extraction and retrieval handle tasks where unstructured information or semantic search can genuinely reduce effort. Workflow and human review control what happens next. The decision interface exposes approved results. The evidence store preserves what is needed to reproduce and defend them. Notice the visual split between deterministic core and AI-enhanced capability. Trust, control, and repeatability belong in the deterministic core wherever possible. AI is used for speed, scale, and insight, not as an excuse to replace explicit rules. This is one of the program's foundational principles. Do not use an LLM where a deterministic rule is safer and simpler. The architecture is therefore not AI first, it is control first, with AI inserted where it improves the operating system without becoming an ungoverned decision authority. Next, we move to deterministic before probabilistic. Let us make that principle operational. Calculations should usually be deterministic. Factors, conversions, allocations, and thresholds need repeatable logic. Validation should be deterministic because schemas, ranges, completeness checks, and source rules are explicit. Extraction from unstructured documents can be AI assisted because variability in layout and language makes fixed parsing difficult. Classification can be AI assisted, but the system should return a confidence score and allow review. Approval belongs to a human gate where uncertainty or consequence is material. Publication should be deterministic plus gated. Only outputs in an approved state become visible to business users. This does not mean deterministic logic is always easy, and it does not mean AI is unsafe by definition. It means the mechanism should match the problem. If a rule can be written clearly, tested, versioned, and audited, use the rule. If the task involves interpreting messy text or retrieving relevant context, AI may add real value, then wrap it in validation, evidence, and decision controls. The question is not can an LLM do this? The better question is should an LLM be responsible for this? Next, we move to requirement to system translation. This slide shows how an FDE decomposes the original TeraWorks request into operating components. Prioritized suppliers becomes data requirements such as spend, activity and emissions, scoring logic, and a category review workflow. Identify data gaps becomes completeness fields and evidence status, rules that detect missing information, and a supplier follow-up workflow. Track engagement becomes tasks, responses, status logic, ownership, and due dates. Reduce analyst effort is not translated into add AI. It becomes a more precise design. Use documents and approved methods as inputs, apply extraction and retrieval, and place the output behind human approval. Defend outputs becomes evidence, lineage, version control, and an audit trail. Operate at scale becomes queues, metrics, alerts, and a support runbook. This is a core FTE skill, translating an outcome statement into data, logic, workflow, controls, and operational evidence. A feature list tells you what the application might show. An operating design tells you how the capability behaves, how it fails, who acts, and what gets recorded. Next, we move to target service architecture. Here is a minimal service architecture for TeraWorks. The upstream layer contains the ERP or spend API, supplier portal, factor library, and document store. Inside the control system boundary, the ingestion service receives inputs. The reconciliation service resolves entities and inconsistencies. The calculation service applies version carbon logic. AI extraction or RAC handles unstructured evidence and methodology retrieval. The workflow service manages state, approval, and exceptions. The output and control layer includes the decision interface, exception queue, evidence store, and audit log. Do not focus only on the boxes. Focus on the promises between the boxes. What does each service own? What input does it accept? What output does it return? What error does it produce? What evidence does it record? What happens if the dependency is unavailable? Architecture is a set of promises. When those promises are explicit, the team can test them. When they are implicit, integration failures become surprises. This is where we move from a conceptual solution into a system that can be implemented. With the service boundaries defined, the next question is how those services communicate and fail safely. A working architecture still needs its components to communicate reliably. This is where APIs and orchestration become central. The service interaction chain runs from an ERP API to a supplier service, then a Carbon service, then a workflow service. Each boundary needs more than an endpoint. It needs a contract, request and response schema, authentication, pagination behavior, idempotency, rate limits, and timeout rules. The second visual is more important than the happy path. A request times out, the system retries under a defined policy. If the dependency remains unavailable, the system uses a safe fallback or holds the workflow. It alerts the correct owner and records the evidence. Then the business workflow runs. Supplier submitted, validate, calculate, check for exception, review, approve, publish. If there is an exception, the flow does not pretend the record succeeded. It moves into a controlled path and returns to review only when the issue has been addressed. The takeaway is simple. A system that works only on the happy path is not production ready. Failure behavior is part of the architecture. Next, we move to API contract anatomy. Let us inspect one API contract in more detail. The endpoint might be get/supplier/ID/emissions. That tells us the interface, but production behavior needs more. Authentication could use OAuth or a service token so access is controlled and auditable. The response schema defines supplier ID, period, unit, and value so downstream services know what they can rely on. Pagination supports scale. Idempotency prevents duplicate processing if the same operation is retried. Retry and timeout policy determines how transient failures are handled. Typed error codes make exceptions loadable instead of leaving downstream systems with an ambiguous failure. A correlation ID links logs across services. These details are not implementation trivia. They are what allow a distributed system to behave predictably. A demo API is often judged by whether it returns a successful response once. A production API is judged by whether it continues to behave safely when the network is slow, a token expires, a record is missing, a page is repeated, or the same request is sent twice. That is the standard the FDE brings to integration. Next, we move to failure path design. This slide makes failure behavior explicit. A request begins with a correlation ID so the transaction can be traced. The service times out. The system retries with backoff, but only if the operation is safe to repeat. If the dependency remains unavailable, the fallback may use a last known value or more safely hold the workflow state. An alert is raised when thresholds are exceeded. The evidence log records the attempt, response, error, retry count, fallback decision, and later review action. The important part is the set of design decisions at the bottom. What is safe to retry? When should the system abstain? Who owns unresolved failures? What output must be withheld? There is no universal answer. The correct decision depends on consequence. A temporary dashboard refresh might tolerate stale data. A material compliance or payment decision may need to stop completely. Failure paths are therefore not a post-launch checklist. They express risk appetite and decision policy directly in system behavior. Next, we move to workflow orchestration with approval gates. Now connect technical integration to business state. A supplier submits evidence and activity data. The system validates schema, source, and completeness. It calculates using the approved method and factor logic. Then a decision point asks whether there is an exception or uncertainty. If there is no material exception, the case can move into review and approval. If there is an exception, the system captures the issue type, owner, due date, supporting evidence, decision, and next action. Only after the state is resolved does the workflow continue. This is why orchestration matters. A collection of APIs does not automatically create an operating process. The workflow layer determines sequence, authority, state, and responsibility. For an FDE, state is evidence. Knowing that a supplier output is approved is useful only if we can see who approved it, under which version, after which checks, and what exceptions were resolved. Good orchestration therefore connects technical state to business accountability. Now that workflow state is explicit, we can introduce AI without making it the architecture. Now we introduce AI into TerraWorks, but notice the title. AI is a component, not the architecture. On the left are useful AI-assisted tasks. Extract fields from supplier documents, retrieve approved methodology, classify documents or activity, summarize evidence, investigate exceptions, and draft communications. These are real opportunities to reduce analyst effort. Across the top is the governed control loop. Start with an approved source. Retrieve and assemble relevant context. Let the model generate or retrieve a structured output. Validate that output against schema, business rules, and confidence requirements. Route the result through a human gate when consequence requires judgment. Only then allow an action. Log the inputs, outputs, and decision. Evaluate quality over time. The red panel is equally important. We deliberately break the system. What happens if the methodology is obsolete, the unit is wrong, the model fabricates evidence, sources conflict, or a supplier document contains prompt injection? The FDE does not ask only whether the AI works on normal examples. The FDE asks whether the surrounding system detects and contains the failure. Components are untrusted by default. Decisions are trusted by design. Next, we move to where AI helps in TerraWorks. Let us separate the useful AI opportunities from the temptation to automate everything. Document extraction can pull supplier name, facility, activity value, unit, and period from unstructured evidence. Method retrieval can find approved methodology excerpts with their source, version, and applicability. Classification can suggest scope, category, or evidence type, but it should return confidence rather than pretending certainty. Summarization can convert long evidence into reviewer-ready notes. Exception triage can suggest likely causes and investigation paths. Draft communication can prepare a supplier follow-up, while a human remains responsible for sending or approving it. The repeated condition across every use case is control. The output should be structured, validated, logged, and reviewable. This is the difference between adding a chatbot and designing an AI-assisted operating capability. The value comes from reducing effort inside a governed workflow, not from giving the model authority it does not need. Next, we move to governed AI control architecture. The governed AI architecture gives us a reusable pattern. First, source, restrict the system to approved documents and data. Second, context, retrieve relevant version material. Third, model, generate structured output under guardrails. Fourth, validation, apply schema, business rules, and confidence checks. Fifth, human gate, approve, edit, escalate, or abstain. Sixth, action, update a workflow or create a work item. Seventh, log, preserve immutable inputs, outputs, and decisions. Eighth, evaluate, measure quality, drift, and failure modes. Notice that evaluation is inside the operating loop, not something performed once during a demo. Models, corpora, suppliers, document formats, and business processes change. Quality therefore has to be observed over time. The phrase at the bottom is deliberate. Components are untrusted by default. Decisions are trusted by design. Trust is not a property we assign to the model. Trust is an outcome of control sources, validation, decision rights, evidence, and continuous evaluation. Next, we move to break the AI system on purpose. A responsible FDE tries to break the AI capability before enterprise users depend on it. Consider the failure modes. The retrieval system finds an obsolete methodology. The extraction model reads tons where the document says kilograms. The model invents a supplier reference. Two evidence sources conflict and the system fails to surface the disagreement. A supplier document contains prompt injection intended to manipulate the model. Or the model produces a highly confident answer from weak evidence. Each failure needs a test response. Curated corpora reduce uncontrolled sources, rich metadata and source versioning allow validity checks. Structured output and schema validation detect malformed fields. Confidence scoring can trigger review. Abstention gives the system permission not to answer. Human approval protects high consequence actions. Evaluation sets measure recurring quality. Adversarial prompts test security and robustness. The key mindset is proactive failure discovery. If you only test the examples you expect to succeed, you are testing a demo. Production readiness requires testing the ways the system can mislead, fail, or be manipulated. A model that is not evaluated is a risk surface, not a capability. Next, we move to human gate design pattern. Human in the loop is often described as a fallback. If the AI is uncertain, send it to a person. That is too weak for enterprise design. A human gate is a control with explicit decision rights. The core statement is machine proposes, system validates, human approves where consequence requires it. The four paths make this concrete. Autocomplete is appropriate when consequence is low, confidence is high, and evidence is strong. Review is used for medium consequence or uncertainty, where a human confirms or edits. Escalate is used for high consequence, conflict, or low confidence, and routes the decision to an expert or governance body. Abstain is a legitimate outcome when purpose, policy, or data is insufficient. A good gate specifies the role, evidence presented, decision right, reason code, service level expectation, and audit trail. This is not anti-automation, it is risk-matched automation. The system should automate confidently where it can and slow down where judgment materially changes the consequence. Governed decisions still need a reliable operating environment, so we now move into deployment and proof. We now leave the development environment and move into operation. The left side shows the deployment and operations architecture. A service is packaged into a container, promoted into an environment, configured with managed secrets, checked for health, and released through CI or CD. Logs, metrics, alerts, and rollback make the system operable after deployment. The failure example is intentionally ordinary. The supplier processing service deploys successfully, but the factor service credentials fail. A naive deployment check might say green because the container started. Observability must detect the authentication errors and elevated failure rate so the team can respond before business users trust incomplete output. On the right is the proof chain. A supplier recommendation can be traced backward through review, calculation, factor version, supplier evidence, source system, pipeline run, and code or method version. These two halves belong together. Reliability without evidence is hard to defend. Evidence without operability is hard to sustain. If a system cannot be observed, it cannot be operated. If an output cannot be reproduced, it cannot be defended. That is the standard for production sustainability systems. Next, we move to from notebook to operating service. This comparison captures the change in standard when a prototype becomes an operating service. A prototype may run locally, assume clean input, use manual credentials, produce minimal logs, focus on the happy path, and have no rollback. That can be completely appropriate during exploration. An operating service is different. It runs in a controlled environment. It handles bad input, secrets are managed, logs, metrics, and traces exist, failure paths are designed. There is a rollback path and a runbook. The mistake is not building a prototype. The mistake is treating prototype success as evidence of production readiness. Deployment is an event. We release a version. Operation is a capability. The system continues to run, fail safely, recover, and remain understandable over time. That distinction is especially important in sustainability because outputs may be reused for reporting, target setting, supplier engagement, investment, or compliance. The system has to remain defensible after the original builder has moved on. Next, we move to deployment environments and CI/CD. A controlled release path protects both the technology and the evidence it produces. In development, teams experiment, run unit tests, and use mock integrations. In tests, they exercise integrations, sample data, and security checks. Instead, they rehearse realistic user acceptance, load, and run books. Production is the controlled environment where monitoring and support ownership are active. Across all environments, secrets should never be hard-coded. Health checks should verify not only that the process is alive, but that critical dependencies are ready. Rollback should be known before release. Release evidence should capture the build, test, approvals, and change record. The deeper point is that production readiness starts before production. If a team first thinks about support, security, rollback, and monitoring at the moment of go live, the design is already late. The FDE brings those operating requirements into the build path early. Next, we move to observability stack. Observability is how the system explains itself when behavior changes. Logs answer what happened, the event, user, source, correlation ID, and error. Metrics answer how often and how much, volume, latency, error rate, and throughput. Traces show where time or failure occurred across services. Data quality monitoring shows which records failed validation or reconciliation. Workflow state monitoring shows where each supplier case is and who owns it. AI evaluation shows whether extraction or retrieval quality is degrading. Evidence lineage shows whether output still trace back to source and method. These layers should not live in separate mental worlds. A user may say supplier emissions dropped unexpectedly. The investigation may begin with a dashboard metric, move to a data quality exception, follow a trace to an upstream API, inspect a model output, and finally confirm a change factor version. If the telemetry is connected, the team can explain the event. If not, diagnosis becomes guesswork. If it cannot be observed, it cannot be operated. Next, we move to evidence lineage for one supplier output. Take one supplier recommendation and walk backward. The business user sees the recommendation. Behind that is the review decision that approved or escalated it. Behind the review is the calculation output. The calculation depends on a factor version and a specific method source. It consumes supplier evidence. That evidence came from a source system record with an extract identifier. The record was processed in a pipeline run with parameters, timestamp, and environment. The logic came from a code build or method implementation version. This backward trace is what converts an output from a statement into evidence. Lineage also allows forward impact analysis. If a factor version is later found to be wrong, we can identify which calculations used it and which recommendations may need to be recomputed. That is why lineages is not merely an audit feature. It is an operating capability for correction, learning, and trust. If the result cannot be reproduced from its source, method, run, and code, it cannot be defended. Next, we move to from assertion to defensible output. Compare the two statements on the slide. The assertion says supplier X has 3,450 tons of carbon dioxide equivalent. It is concise and it sounds authoritative, but by itself it cannot answer basic questions. Which source records were used, which factor, which method version, which calculation run, who reviewed it, what code produced it. The defensible output includes those relationships. The number is connected to source records, evidence files, factor version, method version, calculation run, approval decision, and code build. This is the technical expression of provenance over assertion. Provenance creates the path. Reproducibility lets another person or process recreate the result. Operability allows the organization to maintain, investigate, and correct the system over time. The FDE is not trying to make every screen look more complicated. The user may still see one clean number. The complexity lives behind the interface as controlled evidence. Next, we move to operating ownership model. Technology does not operate itself, so a working system needs named ownership. The data owner maintains source quality and data contracts. The method owner approves factors, assumptions, and calculation logic. The workflow owner defines review gates, service levels, and escalation. The system owner maintains deployment, monitoring, and support. The business owner uses the output and owns the resulting action. Audit or risk reviews evidence, controls, and exceptions. These responsibilities can sit in different teams, and one person may hold more than one role in a small organization. What matters is that the responsibilities are explicit. A common failure pattern is slow operational decay. The system launched successfully, but a factor source changed, an API contract drifted, exceptions accumulated, or alert ownership became unclear. No single component failed dramatically, but trust declined. That is why technology fails slowly when operating ownership is unclear. The FDE should design handoff and ownership as part of the solution, not as an administrative step after build. Next, we move to production anti-patterns. These are behaviors the program wants you to recognize and reject. Do not invent sustainability methodologies silently. Use approved methods and make changes explicit. Do not allow an LLM to override deterministic business rules simply because the generated answer looks plausible. Do not hardcode assumptions without versioning and review. Do not bypass security using demo credentials or shared accounts. Do not hide failed records to make a dashboard look cleaner. Do not deploy without a rollback path. Every anti-pattern has the same underlying problem. It makes the system look more complete than it actually is. This is an important professional discipline. In client-facing work, there can be pressure to make the demo smooth, reduce visible exceptions, or automate more aggressively. The FD has to balance speed with integrity. Working code is not the same as a working operating system. The system must remain safe, observable, explainable, and recoverable under real conditions. Next, we move to the FD principles to remember. We can now summarize 6 reusable principles. First, deterministic before probabilistic. Use explicit rules where they are safer and simpler. Use AI where it adds real value. Second, failure paths are architecture. Retry, fallback, alert, log, and abstain are not support details. They are system behavior. Third, human gates are controls. Approval should be tied to consequence, evidence, and decision rights. Fourth, observe to operate. Logs, metrics, traces, data quality, workflow state, and AI evaluation are features of the system. Fifth, reproduce to defend. Material outputs need source, method, run, and version lineage. Sixth, outcome over artifact. The purpose is not to produce a diagram, model, dashboard, or agent. The system must improve a decision, workflow, control, or sustainability outcome. These principles travel across GHG reporting, EHS, product compliance, circularity, supplier sustainability, and many other domains. The technologies will change. The operating discipline remains valuable. The production principles are clear. Next, let us translate them into the capability stack a learner needs. What capabilities does this role require? The stack is broad, but it is learned progressively. Sustainability literacy helps you understand GHG, ESG, EHS, product compliance, circularity, and supplier sustainability problems. Data skills include SQL, Python, modeling, reconciliation, quality, and lineage. Integration skills include APIs, authentication schemas, enterprise systems, and data contracts. Software skills include services, testing, containers, CI/CD, and security. AI skills include structured extraction, RAG, tool use, evaluation, and guardrails. Operations include logging, monitoring, incidents, runbooks, and rollback. Product and stakeholder skills include problem framing, requirements, communication, trade-offs, and outcome orientation. That list can look intimidating if you read it as you must already be expert in everything. That is not the expectation. An FTE is full stack in orientation, not necessarily a world-class specialist in every layer. The distinctive capability is connecting the layers well enough to move from problem to operation. You do not need to start as an advanced software engineer. You need curiosity, systems thinking, and the discipline to build evidence as we learn. Next, we move to technical readiness scorecard. Segment 0 should help you diagnose readiness, not scare you away. Start with sustainability domain knowledge. Can you explain a basic reporting, compliance, EHS, carbon, or supplier sustainability problem? Next, data literacy. Can you reason about tables, identifiers, units, and data quality? For SQL and Python, can you manipulate basic data or at least read and adapt simple scripts? For APIs, do request, response, authentication, and error handling make sense? For AI systems, do you understand the difference between retrieval, extraction, validation, and review? For deployment, do containers, logs, health checks, and rollback make conceptual sense? Rate yourself as foundation, working, or strong. The score is not a credential and it is not a reason to reject yourself from the pathway. A readiness gap simply defines your preparation plan. Someone with strong sustainability knowledge may need more coding and API practice. A software professional may need more methodology and evidence literacy. The goal is to enter segment 1 knowing where you need support. Next, we move to pathway diagnostic, FDE, or sustainability product management. The hub should route learners to the transformation that fits their motivation. Listen to the questions you naturally ask. If you keep asking, what should we build first? How should this be prioritized? What value proposition wins? You may have a stronger sustainability product management orientation. If you keep asking where does the data live, what breaks in production, how will the systems connect, how do we prove the output, you may have a stronger FTE orientation. Some questions matter to both roles. How do we prove the output is one of them. Product needs evidence that the capability is useful and trustworthy. FTE needs evidence that the system behaved correctly and can be reproduced. There is no better or worse choice. The value of the diagnostic is avoiding a program mismatch. A person who loves product discovery but hates troubleshooting integrations should not be forced into an engineering identity. A person who loves making systems work should not be confined to strategy slides. Segment 0 develops the implementation path while respecting the product pathway as a sibling profession. Next, we move to product FTE collaboration model. The strongest sustainability technology teams need both product and FTE in the operating loop. During problem discovery, product management may lead customer and user understanding while the FDE tests enterprise feasibility. During requirement framing, product defines user value and priority while the FDE defines system obligations, data dependencies, controls, and failure conditions. During build design, the FDE shapes architecture while product validates whether the build still serves the intended outcome. At release, product looks at adoption and user readiness. FDE looks at technical and production readiness. During outcome review, both examine value, evidence, and operational improvement. The collaboration principle at the bottom is worth remembering. Product determines whether the capability deserves to exist. FDE ensures the capability can actually operate. In real organizations, the boundary will not always be neat. What matters is that both sets of questions are answered. Otherwise, teams either build the wrong thing well or define the right thing without a viable implementation path. Next, we move to Human Gate Capability Map and Segment 1 Bridge. This slide brings the Masterclass together and turns it toward action. On the left is the Human Gate, machine proposes, system validates, human approves where consequence requires it. The 4 paths, autocomplete, review, escalate, abstain, show that governance can be designed into workflow rather than added as a manual safety net. In the center is the FTE capability stack. Sustainability literacy, data, integration, software, AI, operations, and product or stakeholder capability. Segment 1 does not assume mastery of every layer. It begins the process of connecting them through hands-on evidence. On the right is the 5-day builder challenge. Day 1 is reconcile, day 2 is integrate, day 3 is build, day 4 is deploy, day 5 is prove. Each day produces a portfolio output, not just a completed lesson. The same 5-stage ribbon that opened the masterclass now becomes the learner journey. No is no longer enough. The next step is to make the TeraWorks capability work, observe it under failure, and defend the evidence it produces. You have watched the requirement become a system. In segment 1, you build it. The pathway is now clear. The final section shows exactly what the learner builds in the 5-day segment 1 sprint. Day 1 starts with the foundation, enterprise sustainability data. You will load mock ERP, supplier, and factor datasets. Then you will create a canonical supplier and activity schema. You will apply completeness, unit, and period checks. You will reconcile identities and compare facts across sources. Anything that cannot be safely resolved will move into an exception queue. The portfolio output is an enterprise sustainability data pipeline. The evidence is more important than the code alone. Schema, reconciliation logic, data quality report, exception register, and a short walkthrough explaining the decisions. This data directly applies the integration principles from TeraWorks. The goal is to experience what happens when the supplier data turns out to be multiple inconsistent representations. By the end of day 1, you should be able to explain not only how you cleaned the dataset, but why your controls make the resulting facts more trustworthy. Next, we move to day 2, integrate. Day 2 turns reconciled data into connected services. You will define an API contract, endpoint, schema, authentication, and error behavior. You will connect to mock ERP and supplier APIs. Then you will handle pagination, retries, rate limits, and timeouts. You will add correlation IDs and logging so requests can be traced. Finally, you will write a runbook that explains how to operate the integration and diagnose failure. The portfolio output is an API integration service plus runbook. The evidence includes an open API contract, integration test results, retry behavior, error handling, and operational guidance. The learning objective is not call an API, it is to make an integration predictable under normal and abnormal conditions. This is the move from code that connects once to a service that can be operated repeatedly. Next, we move to day 3 build. Day 3 introduces governed AI as part of the TerraWorks system. You will curate approved context, methods, evidence files, and metadata. You will extract structured fields from supplier documents. You will build retrieval over the approved methodology set. Then you will validate outputs using schema, rules, confidence, and source checks. A reviewer will approve, edit, escalate, or abstain. The portfolio output is a governed sustainability AI service. Evidence includes prompts or model instructions, structured schemas, validation behavior, an evaluation set, failure tests, and a human gate decision log. The point is not to prove that an LLM can read a PDF. We already know it can. The point is to prove that the AI capability operates inside a controlled loop and fails in a way the system can detect and contain. That is the difference between an AI demo and an enterprise AI component. Next, we move to day 4, deploy. Day 4 moves the system from local execution toward an operating service. You will package the service in a container, configure environments, manage secrets, and use either CI or CD or a documented release path. You will add health checks, logs, metrics, and alerts. You will define a rollback and incident response path. The portfolio output is a deployed sustainability service plus monitoring pack. Evidence includes the container configuration, deployment guide, health checks, logs, alert rules, and rollback notes. This day teaches a professional threshold. It runs on my laptop is not the end of implementation. You should finish day 4 able to explain how another person would know whether the service is healthy, what they would do when a dependency fails, and how they would return to a safe version. Next we move to day 5, prove. Day 5 closes the loop with evidence. You will run an end-to-end supplier scenario from input to recommendation. Then you will deliberately inject a failure, perhaps a broken API, missing evidence, or incorrect unit. You will diagnose the issue using logs, metrics, and exception records. You will apply the correct control path and human gate. Finally, you will trace the output back to its source, method, pipeline run, and code version. The portfolio output is a production readiness and technical evidence pack. Evidence includes the end-to-end demonstration, incident notes, lineage trace, tests, governance controls, and a readiness summary. The key word is defend. The final exercise is not simply to show that the system worked. It is to show why you believe it worked, how you know what happened when it failed, and how another person could reproduce the result. That is the meaning of proof. Next, we move to segment 1 connects to the full technical bootcamp. The 5-day sprint is an entry point, not the whole technical journey. Workshop 1 deepens enterprise data reconciliation. Workshop 2 expands API integration and enterprise system simulation. Workshop 3 develops cloud deployment fundamentals. Workshop 4 focuses on structured LLM extraction with schemas, validation, abstention, and audit logging. Workshop 5 builds RAG from scratch and evaluates retrieval. Workshop 6 develops workflow and tool orchestration with state and human approval. Workshop 7 moves into an enterprise platform sandbox with data models, workflows, permissions, and architecture. Workshops 8 through 11 extend implementation, operations, and capstone evidence. The important design choice is continuity. Segment 1 is not a disconnected teaser. It induces the same skills that the bootcamp later deepens. The learner therefore moves from curiosity to implementation evidence, then from implementation evidence to a broader professional portfolio. Next, we move to portfolio evidence standard. This program does not define completion as watching content. A strong portfolio includes a problem statement that explains the decision, workflow, and user context. It includes a data model with source ownership. It includes integration proofs such as API contracts, tests, and runbooks. It includes AI or logic evidence, rules, prompts, evaluation, and validation. It includes deployment proof, environment, health checks, monitoring, and rollback. It includes evidence lineage from source to output. It includes a recorded demonstration that shows a scenario run and failure handling. And it includes a reflection on trade-offs, assumptions, and next improvements. This standard changes the learning behavior. The question stops being, did I finish the module, and becomes, what can I show that proves I can perform the capability? A portfolio is valuable only when it demonstrates how the system works and why it can be trusted. That is much harder to fake than content consumption, and it is much more useful in interviews, consulting discussions, and internal career transitions. Next, we move to role fit self-assessment. Before choosing the pathway, assess motivation as well as current skill. If you enjoy debugging messy systems, that is a strong FDE signal. If you want to connect domain knowledge, data, and software, that is another. If you can tolerate ambiguity while building evidence, the role is likely to feel natural. If you care about auditability, controls, and understanding why an output is true, that also aligns strongly. If you prefer strategy, product decisions, customer discovery, and prioritization over implementation, the sustainability product management pathway may fit better. If you currently avoid code, APIs, or troubleshooting completely, that does not automatically exclude you, but it does mean a foundation sprint is necessary before the FTE build work. The right learner is not necessarily the most technical person in the room. The stronger signal is whether you want to make systems work and are willing to build the technical capability required to do that. FTE fit is a combination of motivation, systems thinking, and readiness. Next, we move to 30-day technical preparation roadmap. If the readiness scorecard exposed gaps, the preparation roadmap gives you a practical way to close them. Week 1 focuses on data foundations, tables, identifiers, joins, units, quality checks, and lineage. Week 2 adds Python and SQL practice using sample sustainability data. Load it, clean it, transform it, validate it, and reconcile it. Week 3 focuses on APIs and services, request and response, authentication, JSON, errors, retries, and simple endpoints. Week 4 introduces AI and deployment concepts, structured extraction, RAG, validation, containers, logs, and health checks. The goal is not to become an expert in 30 days. The preparation output is more modest and more useful. You should be able to read basic code, inspect data, understand an API response, and explain why evidence lineage matters. That foundation is enough to enter segment 1 ready to learn by building rather than being blocked by every technical term. The preparation path is complete. We can now close by returning to the thesis that opened the masterclass. We end where we began. When content becomes cheap, technical differentiation moves from knowing to integrating, building, deploying, and proving. Know means understand the requirement and the concepts. Integrate means connect real systems, data, identities, and constraints. Build means create working services, rules, workflows, and governed AI capabilities. Deploy means operate them reliably with security, monitoring, and recovery. Proof means defend the output with evidence, lineage tests, and measurable outcome. Over the last 90 minutes, TerraWorks has moved from one deceptively simple business request to a complete operating model. Source systems, canonical data, reconciliation, APIs, deterministic logic, AI assistance, workflow, deployment, observability, human gates, evidence, lineage, ownership, and portfolio proof. That is the role. The forward deployed engineer for sustainability is valuable not because they can describe what a sustainability system should do, but because they can make it work in the real world. Segment 0 was designed to help you see the path. Segment 1 changes the mode from observation to implementation. You have watched a sustainability requirement become a working enterprise system. Now you build it. Closing delivery note, recommended final pause. After the final line, leave 3 to 5 seconds of silence on the closing slide before ending the recording. This gives the segment 1 call to action room to land without adding a separate sales pitch.